Good afternoon, Oslo. Thank you for having me here. I decided that it would be fun to talk about a very boring subject by injecting a little bit of Hollywood. So, hence the name of this talk, which is Back to the Future Time Series Data. And I'm a huge Back to the Future fan. If you're not, I'm sorry, this is probably not the talk for you. How many of you have actually messed around with time series data? Oh, all of you. You don't need this. This is a good introduction talk. Pretty much the way that I go through this is what I experienced when I moved from a relational database decade over to time series data and how I had to think about it and explain it to others, right? Okay, so let's talk a little bit about what we'll cover today. Obviously, we're going to go through some time series data stuff. I'm going to focus on the past analysis aspect of it, the present monitoring, and of course, future predictions, hence past, present, and future. And of course, we'll go through a little bit of a technical demo. Here, I'm going to go ahead and do just what it kind of looks like to dashboard out if you had 10 DeLoreans at once that you were monitoring. And that's kind of our fun technical demo at the end today. All right, so let's talk about a little bit about the fundamentals of time series data for those of you who have never done it before. I was definitely one of those people. So what exactly is it? I mean, simply put, it's just a sequence of data points that is collected at regular intervals over time. It's an ordered collection where each value is associated with a timestamp. So if it's a timestamp-based analysis that you're going to do, this is probably the format you're going to do it in. Think of server metrics or sensor readings, stock prices, and application events, anything measured repeatedly over time. What makes time series data special is that time itself becomes your primary axis for analysis. And it creates kind of an importance between how often you take a snapshot of that data. Right. This time-based relationship creates unique challenges and opportunities. The first time that I actually did something with this was in the aviation industry. We were interested in doing snapshots of time when a drone was moving from one end to the other and what it was doing in between in terms of not just GPS location, but how the rotors were spinning, if there were any sort of anomalies that were being detected, et cetera. I went from doing e-commerce websites to that. It is a really big shift because suddenly everything you do in your code matters tremendously, right? Everything you do when you're reading and writing matters tremendously because if you're waiting for any sort of self-healing processes or anything that has to do with making a change in real time, the stakes are just higher. Now let's talk about one of the biggest challenges with time series data, and that's high cardinality. So high cardinality is a term that sounds really complicated, but the concept is simple. Each unique tag combination creates a new data point, right? For example, imagine you're tracking a server, like a server, different server metrics. If you tag by hostname, application, region, and customer ID, you might suddenly have millions of unique combinations of that. Each one requires storage and indexing, which affects your database performance, right? High cardinality can lead to really increased storage costs and slower query processing and visualization changes. Kind of like trying to generate 1.21 gigawatts of power. Without the right approach, you're just not going to be able to handle it. So taming cardinality is one of the key takeaways today, and we'll see how modern time series databases can make that manageable. I know that when I started looking into this, I had never heard of high cardinality because, again, I was probably more used to relational data that didn't need to be real time. It was stuff that wouldn't change necessarily all the time. And the first time I dealt with this was, again, when we looked at multiple servers. And I think at that point, I had to completely scrap the way that I wrote the code for it. All right, so today what we're going to do is a combination as an example. I'll just use InfluxDB, a company that I work for currently, and .NET because we're here at NDC Oslo. And I'll use Grafana for visualization, but you could just as easily use Power BI or Tableau or any other kind of visualization platform of your choice. I know the platform of my choice sometimes is to just spin up a React app and visualize that, but I figured this would be a little bit easier to put the pieces together. All right, so let's analyze the past in this time series data world, right? Let's journey back to 1955. Magnetic tape was the primary storage medium. Punch cards were used for data input and storage. And of course, storage space was very expensive and limited. And data analysis was extremely time-consuming. If you look at the historical data, it poses unique challenges. Because in the early days of computing, we had all of these limitations, but today we have different kinds of challenges. We can store petabytes of data now, right? But efficiently querying and analyzing it is pretty much the reason why you'd want specialized kind of time tools. You can use multiple different kinds of time series databases. There are several out there, but that's the reason you might want to choose one over making that approach with a more traditional database. One of our key takeaways is just learning to read time series data efficiently with SQL, and Influx supports SQL queries, so does several of the other ones out there. It just makes it a little bit more accessible if you're used to only doing SQL. Before this year, apparently, usually it was a different kind of query language that you would have to learn. And while that can be really helpful, sometimes it's hard to share amongst your entire team. So it's nice that most of the time series databases now can use SQL. At least for me, who has been doing that for about 12 years. So here are some considerations that are kind of crucial. You need to think about using time bucketing or aggregation to reduce data volume. For instance, rather than querying every second of data over a year, maybe aggregate into hourly or daily buckets, and always limit time ranges in where clauses to improve the query speed. That ensures you're only scanning relevant data. I can't tell you how fun it was the first time I just selected star from the entire database. That was fun for me. Let's see. I just lost my, there we go. Yay. Also, consider creating specific indexes for frequently queried fields. I know that really helped a lot with my recent project. And again, don't select star. I really did this by default probably the first 5 years of my life as a programmer, and it didn't serve me well when I moved over to time series. Here's a good example of that. So here's a good example of a query that you might want to put together that would be a little bit more performant than what you would expect otherwise. It shows the principles in action. We're using time bucket to aggregate by hour, selecting specific fields, filtering by location and specific time range, then grouping and ordering our results. These optimizations can turn a query that might have taken minutes into one that completes in about 600 milliseconds. Of course, that does depend on how much data, right, that you have in there. Most of what I run into now is real-time or historical captures, which was real-time, which means you might have an incredible amount of granularity inside of your data. All right. One of the most valuable aspects of time series analysis is finding patterns in historical data. Just like dance rhythms, all of these have patterns, you know. Time series data follows identifiable patterns as well. There are several techniques we can use to detect the patterns. Correlation helps us find relationships between different metrics. For example, does the CPU usage correlate with memory consumption? Trend analysis uses moving averages and helps us spot longer-term directions in our data, smoothing out short-term fluctuations. Something I'd never heard about before moving into this world was seasonality. But seasonality identification helps us spot repeating cycles in data, like daily usage patterns or weekend versus weekday, something that might happen only in the summer versus the winter. And this is something that traditionally you've been able to pull out. After the fact, you can look at that with as a data scientist. But as a developer, if you are aware that these are going to be requirements in the future, it'll help you tame and capture that data a little bit easier to be more performant. By identifying the patterns, we can understand normal behavior versus anomalies, predict future trends, and make better decisions. As we collect more and more time series data, managing database growth becomes kind of important, wouldn't you say? This slide addresses another key takeaway, which is handling scale from thousands to millions of data points. I'm sure plenty of you have done this, but I had never done it. So I really wanted to lay it out for myself in the past. You need to make strategic decisions about data retention, okay? Keep raw data when high precision is needed or for regulatory requirements. This is something that I ran into quite a bit, again, in the aviation space, but that also might be the case for you if you're a bank, right? So you might have to retain a certain amount. I know GDPR is a really big part of Europe, and sometimes you have to keep a lot of very fine-grained data for many years at a time. So only when you're required to do this do you keep that level of data. There are several techniques for kind of efficient data management here. You can aggregate it when you're analyzing long-term trends to take down your storage costs. I know that for example, if you no longer need your real-time data because that day has passed, perhaps maybe 24 hours after your real time, when are you going to want to look at it again? And so often you'll find moving it into a zip file or moving it into an automatic ETL process to cold storage just makes more sense. Or even just leaving it where it is, but then taking a snapshot of that and moving it over to something like Snowflake also makes more sense to be able to analyze while you're still dealing with the fine-grained real-time data. Consider data access patterns when you are deciding some of this stuff. Compression uses specialized algorithms that is optimized for time series patterns to reduce storage. And it's pretty easy to do in Influx, but it's the same across many of these databases. A multi-tier architecture balances performance and cost, giving you fast access to recent data while efficiently storing historical information. Honestly, the right approach kind of depends on your use case. And that's something that I would love to hear what kind of use cases you all have had. But I suspect it might be one or two of the following. Have you dealt with time series data in finance? Yes? No? Just a couple of you? All right. How about Formula One? No? That's the fun stuff. I love things that are done at speed. Anybody in the space industry? Huh? So satellite tracking is another one that's done often. Something that I ran up against a lot is that, I had come from an e-commerce background where I would build a lot of things with inventory management, and we would have a lot of sales every second, but it's not the same as tracking satellites across the sky, right? That's just a different level of redundancy and speed that you need. I also found that I had to move out of thinking that I was cloud connected at all. A lot of time series data really shines when it's done locally. Very fun to do that. The great news about that is I never have to worry about an internet connection whenever I'm testing things out. But it is different when you're trying to figure out when do you sync an edge device. How often can you do that? Does it talk to its neighbor? That's a completely different way to think about architecture, and it's probably one of the biggest reasons that it drew me in to time series data. And of course, downsampling is the reduction of the older data. Compression we went over. Cold storage, you know a little bit about that. and just balancing the cost of multi-tier architecture, okay? So this is a different way to think about how to balance it. All right, so that's some of the historical stuff. What about doing things right now in the present? Let's travel to November 5th, 1985, or May 22nd. That works too. It's our present day analogy for real-time monitoring. When Doc Brown was trying to harness lightning to power the DeLorean, he had to have precise real-time monitoring. It's essential, right? And real-time monitoring requires efficient data writing. It's a really big deal. So we're going to efficiently write with something called line protocol, which is Influx's format for writing time series data the fastest possible. You can do it in an SDK, you can do it in an API call. This is just one of the ways that you can get data into and out of a time series database like Influx. And then you have to consider your edge device, or in this case, it might be the DeLorean, right? Analyze data closer to its source so you don't have to worry about the latency so much. It will kind of go like this, like a measurement, a tag set, field set, and a timestamp. And most of these are key value pairs, for those of you who have never seen it before. So let's take a look a little bit at what it looks like to use line protocol as a call in to gather that data and to push it into the database. Get back. There we go. The example's always at the bottom. Right. All right, so here we're looking at a pattern that's just the basic measurement set and field set. So it's not unlike JSON or XML. Line protocol uses simple comma-separated key-value pairs. This is probably the least amount of code that you will write if you use this protocol. It significantly reduces overhead. I've tried multiple ways to get it in, and this just is the fastest. It's smaller in size, and it's just faster to parse. So let's look at the example, and the single line contains the measurement name, location, and driver tags, the speed and power level fields, and of course, a precise timestamp. Compare this compact format to, let's see if I can find it here. Compare that format to just the equivalent JSON, which would just be much more verbose, right? It would just be a lot longer. The efficiency becomes pretty important at scale, depending on how often you're writing it. The last piece of code that I wrote, and pushed things in every 100 milliseconds, so you can do the math from there. While line protocol is already efficient, we can further optimize through batch writing. Instead of sending each data point in a separate HTTP request, batch writing groups multiple points into a single write operation. It's just a better way to do it. And this approach already dramatically reduces all of the throughput hugely. And of course, the snippet that you're seeing over here kind of demonstrates how to implement that basic batch writing. And it includes some error handling just a little bit there. For optimal performance, you'll want to adjust the batch size based on your specific network. And if you get too small and you're not really getting the benefit of batching, but if it's too large, then you might encounter a lot of timeouts, etc. Don't forget that robust error handling is crucial. The amount of times I've just not captured something because I didn't handle it well is endless. So remember, writing data efficiently with line protocol is probably a little bit of a learning curve, but it's not too bad once you get going. All right, so here's the two compared to each other to really appreciate it and the differences between them. So yes, it has just these two differences really sped up the kinds of writes that I was doing. The size difference directly impacts your network transfer times as well, parsing speed, and storage. So when you're dealing with millions or billions of this, it's suddenly very important. This efficiency just isn't about saving storage, though. It translates directly into better performance while you are going. So in real time, that means that you will be able to see whatever is going in and query it back much faster as well. All right. Let's tackle one of the most important challenges in time series data, high cardinality. Remember, that means a couple of things. It means that you have to worry about multiple combinations, overwhelming, and making your queries slower and slower and slower when you go to actually read this data. There are several techniques to manage that. First, you have to be strategic about your tag selection. It's a big deal. Keep high cardinality fields as values and not as tags. That's probably the biggest difference in architecture that I see, is once you move over to values, it does come much more smoothly. For example, if you store the user ID as a field value rather than tag, that is the example that prevents the explosion of the index size itself, right? Second, you need to create structured tag hierarchies, okay? Group-related dimensions like region or data center or rack, for example. This lets you query higher levels first and then filter down, reducing query scope just kind of progressively, right? Third, you need to use structured time bucket aggregation. Pre-aggregate your data by time windows for frequently accessed data, and like maybe doing 1-minute roll-ups, right? Okay, and then fourth, write shard-aware queries that limit time ranges to target specific shards. Use like time is greater than now. Instead of unbounded queries to avoid scanning unnecessary data blocks. At first you might do this and wonder what is going on, but these are specific techniques that I've used to help bring all of that down and bring the noise down. These techniques directly address our first takeaway of how to handle high cardinality and ensure that your time series database remains performance. Okay. Do I have any questions on this? Good? All right. Let's move on to the future. Yes? Awesome. Let's travel to 2015. Wasn't that long ago, was it? The future in our Back to the Future movie. Okay, so the key is using patterns detected in historical data to make informed decisions about predicting the future. That's simple forecasting. So this is not exactly using data science. It's just simple analysis to go forward. It can be done with moving averages or linear regression. In our dashboard, we'll be able to project fuel consumption rates by calculating the average decrease in plutonium levels over time, right? And then extrapolating to predict when we'll reach a critical threshold. And this is just some basic stuff. Obviously, we have come a long way now in doing predictive analysis, but this is just one way the time series is used for that purpose. Grafana uses built-in functions like trend or predict linear that can visualize future values based on recent data points. And Influx also provides moving average calculations that smooth out the data and reveal directional trends. For predictive maintenance, we can correlate engine temperature and power level patterns. When we see a specific combination trending upward, we can predict potential issues before they cause breakdowns. Resource planning becomes a lot easier when we understand consumption rates. By analyzing how quickly something like Mr. Fusion depletes plutonium during different types of time travel, we can predict exactly how much fuel we'll need for future trips, right? And finally, anomaly detection. It establishes a baseline pattern of normal operation, and it allows us to identify unusual patterns early. For instance, if the time circuit's voltage, if it kind of goes out of whack and it starts fluctuating in an unusual pattern, we can predict potential failures before they occur based on what we've seen before. And I'm sure plenty of you have done something like this. Yeah? Some of you have done a little bit of future predictions? A couple of you, yes. It does make it a lot easier, and it isn't just based on the platform. If you don't have your data in this format, it becomes really difficult to do any sort of future prediction. Now, can you take relational data and can you make future predictions? Some of it. It depends on how often. For example, if you have something that doesn't change a lot, it might not be suited for time series data analysis, and yet you might find yourself with a lot of historical data that's in that format. You'll need to apply the same pattern. The biggest thing you run into is that there'll be these holes where you need to be able to smooth from one value to the next, and that interpolation is something that I never really dealt with that much when I was doing traditional SQL Server work, but I definitely do now. The biggest example I have of that is, aircraft black boxes, the ones that collect all of the data from the cockpit and all of the instrumentation on board the plane, so that if something were to happen to the plane, eventually they retrieve the black box, and it's not black, it's actually orange, but I digress. They retrieve it to look at, over time, when did something change in the engine, when did something change in the pitch or roll or yaw of the aircraft, all of that information. In order for it to be played back, you have to do it smoothly. Otherwise, you won't really know what point in time the aircraft was at. And going smoothly from this data point up to this data point is called interpolation. And the interpolation in taking traditional relational database data, unless you have a lot of it, is a big guess. It's a big guess about was that a smooth transition over the past few months, or was it the past few minutes? That's why it's just a little bit easier to think timestamp first when you want to store this kind of data. The other example I have of this is moving stock prices, right? So if you are trying to create a platform that monitors them over time, you want to be able to see if you can predict the way that things are continuing to go. And if you don't take enough snapshots of it often, and you don't have enough historical base for it, you don't really know, is the stock really dropping a lot? Is it really going to continue to go to the moon? You need to have enough of this. And by saying enough of this, you're going to have to start storing a lot, and it becomes very expensive to do it. Usually, time series databases are just set up to be a lot less expensive for you to do that way. Now it's time to pull everything together with our DeLorean dashboard demo, okay? I've created a monitoring system for the time machine that demonstrates all three aspects of our key takeaways, right? It has the past, which is going to be analyzing velocity patterns and time circuits voltage stability over time. It shows how historical analysis can reveal patterns and trends. For the present, we're monitoring the flux capacitor power and engine temperatures in near real time, demonstrating efficient data writing and reading. For the future, we're going to predict time travel events at 88 miles per hour and managing Mr. Fusion fuel reserves, showing how time series data can help with forecasting. And the dashboard isn't just for show, it really demonstrates real techniques for working with time series data using .NET. And I have this also checked into a GitHub repo for you too if you want to play around with it later. But I figure we could also just go through the architectural flow. Our .NET application generates simulated DeLorean metrics, everything from that velocity to the power levels. And we're basically just taking inputs, putting them into some time series database, and then using a visualization platform. And it kind of looks like this time, but it could also be any other branded combination. The beauty of the setup is the simplicity and scalability. The same architecture works whether you're monitoring 1 DeLorean, 10 DeLoreans, and you're on Influx or something else. All right. That's probably my favorite slide of the whole demo. All right, let's see if we can get this started. Nope. I have lost. There we go. All right, hopefully you guys can see my screen here. All right, everybody can see? Yeah? Sweet. Okay. Let's first look at the data generator behind our dashboard. That's the program.cs file in our .NET application. All right, I'll go here. If you notice, I'm actually running it right now. Yeah? That's because I already have, let's see, pull up this. Sorry, I have to keep pulling it over here. That's because this is what it is populating. This is what we have built here. Right now I have a refresh rate set to every 5 seconds. That's about the fastest you can do with Grafana Cloud, but you can go faster if you wanted to do a local version of that as well. This just shows the last 15 minutes or so of data. I can also change that if I wanted to be a little bit faster, and kind of shows you the differences here. All right. So yeah, it's kind of a fun visualization of all of that data coming in. This is also the combined engine temperatures of 10 DeLoreans. They're running kind of decently warm. I really should put Celsius on there though if I'm going to do this in Europe. And this is the current speed. If you notice, they will ramp up, hit the lightning, and go back down again. It looks like currently the fuel level is at 62.6%. And you see the velocity, and of course, where the flux capacitor power is at the moment. All of these are data points that are coming in and that I am gathering in real time here. You too can go to this link if you'd like, and it's currently running. All right, so let's go back to our program walkthrough. Okay. Sorry, I'm going to have to go back and forth here. All right. Our DeLorean monitoring system uses a background service that continuously generates and sends time series data points to Influx. So we set up the connection parameters, including the Influx URL and such right here. Maybe don't take a picture of that. But all of this you can get when you sign up for, I'm using Influx Cloud. You can also use a localized version of that. And this is just calling to its write API using line protocol with my org and my bucket. My bucket is basically just the database name itself. All right, and if we go to our doubles here, here's my simulated data parameters that I've got going on. For our demo, we have several key metrics: velocity, power levels, temperature. And in a real-world application, these would be actual sensor readings that would be coming from your sensors or your application metrics. And each of these represents a distinct time series that we track over time. Okay? All right. Now, if we look at, I'm so sorry, this is not, there we go. All right. If you notice, we are defining several dimensions that could combine to create high cardinality. With 5 DeLorean IDs, 5 locations, 4 time periods, and 5 drivers, we could generate up to 500 unique combinations. Yes? This demonstrates how quickly cardinality can explode with multiple tag dimensions. Specifically, this exploded with my drone demo that I was working on because I would have to do zones that the drones would be flying through, but I'd have 10 at a time that would be flying, trying to map out just the area at the time, and then suddenly trying to keep track of everything. It just exploded. What time of day did we fly over it? Did we make more than one pass, etc. All right, and then we have an execution loop in here. Right? It's pretty easy. This is our main execution loop that runs every 5 seconds. So for time series data, the collection interval is crucial, very important. If you have it too frequent, and you're going to overwhelm your storage. And if it's too infrequent, and you might miss a couple of very important patterns. For our DeLorean metrics, the 5 intervals provide a pretty good balance, I think, at the moment. Although I have brought this down to 50 milliseconds, and that was interesting how quickly that exploded. All right, for our line protocol formation, there we go. I think I'm getting the hang of this. Let's go down to the power level. Yes, for our generate and send data. Okay. The basic metrics are low cardinality. They wouldn't take a lot there. Creating the line protocol format we discussed earlier is what this is doing, if you notice. Each line follows a pattern of measurement, tag underscore key equals tag, value, field underscore key equals field value, and timestamp. Notice how we're structuring the data with a consistent measurement name, DeLorean stats, okay? And using device as a key tag to differentiate each of the metrics. And this is the best practice that makes querying so much more efficient, so we can filter by this tag. The timestamp at the end is in nanoseconds, and since we're using the Unix epoch, which is Influx's highest precision that you can go. We're generating this by converting milliseconds and multiplying by 1 million. Okay, good. All right, and then here for the high cardinality generation, for each data generation cycle, we create 20 data points with randomly selected combinations of the DeLorean ID, location, and time period to drive and the driver as the tags. So this results in many unique tag combinations, exactly the high cardinality challenge that we discussed earlier. Notice that we're using a separate measurement name, which is DeLorean detailed, to isolate the high cardinality data from our primary metrics. So we can decide what are we going to pull into cold storage, what are we not. So we've already started thinking about how we're going to view this data and how to store this data even inside of our loop itself. All right, come back over here. There we go. All right, and if you notice, remember I mentioned about batch writing. That's what we've got going on here. This is our batch writing implementation. So instead of sending each line separately, we join them with new lines and send them as a single HTTP request. This batch approach significantly reduces network overhead and is essential for high throughput time series data collection. All right, so here is the sending to Influx. Let me get that back here. Where did it go? There we go. All right, the send to InfluxDB method, we're going to send the data to Influx using that HTTP API, and you can notice a couple of important details here. We're specifying NS, which is nanosecond, precision in the URL itself. The authentication is handled with a token at the authorization header, and the content type is text plain for the line protocol data type. So if you're going to write with line protocol, that's what you will use, is text plain. And we have error handling, and we can log any failures that we got from here. This robust implementation ensures that our time series data can reliably make it into our database, even at high volumes. All right. Do I have any question with this? We're good? Yes? Okay. Awesome. Let me see if I can pull up our Grafana dashboard, though, and bring this over. All right. Now let's look at the Grafana dashboard and the SQL queries behind each of the panels. This will demonstrate the reading with SQL aspect of our key takeaways. I also checked this into the GitHub repo, so you can just grab it and throw it up yourself. You don't have to handcraft them. And I will put it here. So let's go to, I think this is the one we're doing. Let's go in here and take a look. Let's see, the flux capacitor maybe? Let's see. Yes. If you notice down at the bottom, can you see that? All right. This is the gauge that shows the current power level of the flux capacitor. It's pretty important for time travel. And here is the SQL that powers it. This query demonstrates several best practices for time series SQL. We're selecting only the specific fields that we need, like time and power level. We're filtering by the device tag to target only flux capacitor data. And most importantly, we're using a time filtered to limit the query to the last 15 minutes. That's the default. If you notice, I also changed the dropdown to 5, which will override the amount of time. But this is the base default one. That time filter is pretty important for performance. Without it, the database would need to scan all of its historic data, which could be enormous in a real-world application. All right, let's go back to the other one. All right, let's look at the velocity chart. I think that's a fun one to do. Right. This one shows our velocity over time with the critical 88 miles per hour as the threshold that is marked. This is the query for that. Again, notice the tight time filter of 15 minutes. We typically only need recent data for this because we're monitoring this DeLorean in real time. In Grafana, this time range can obviously be adjusted, but having that default is pretty crucial. All right, and then the time circuit stability. Oh no, the data is outside the time range, fun. All right. This chart tracks voltage fluctuations in our time circuits, so it's kind of important for accurate temporal navigation. The consistency across these queries kind of shows the power of using a data model in this way. If you use device as a tag, you can easily filter specific components of the DeLorean itself. And this is much more efficient than using separate measurements for each device type. Come back over here. Good to you. Where is Mr. Fusion level? Ah, yes, this one. Okay, this gauge shows the current plutonium level in our Mr. Fusion reactor. Again, it's the same pattern of targeted field selection, tag filtering, and time bounding. All right, so that's our fun dashboard there. Let's see. Let me go back to my deck. Do I have any questions about the demo? We're good? Awesome. Let's see. All right. Man, I have completely lost my slide deck. 1 second. All right. I've got it. Woo. All right. All right, here we go. If you'd like to explore the demo further or build your own time series stuff, I definitely have a repo for you if you're interested in that. But let's talk a little bit about predictive maintenance alerting. I didn't have this in our dashboard, but it kind of demonstrates some important concepts here. Okay, our predictive maintenance query uses the derivative function to calculate how quickly the engine temperature is rising. If it exceeds 2 degrees per 30 minutes, we can predict overheating before that happens and alert that maintenance is needed. Here. Right. The plutonium consumption forecast is something that's even more practical. It predicts when we'll run out of it. So it gets our current plutonium levels and then calculates our hourly consumption rate, then divides the level by the rate to determine the hours until empty. It was fun to do this. I can't wait to add more aspects to this. And if you have suggestions for what might be even cooler to monitor, please tell me, and I'm happy to build up the demo even more. But if you notice, no machine learning is required for this. Just simple time series functions that leverage basic patterns in data to make practical predictions. This demonstrates that if you host your data in time series format, it's not just about like the past and present, it's also about the future and the patterns looking into it. If you're interested in that GitHub repo, I have that here. I also have added a complete demo replication guide. So if you want, instead of just forking the repo and going ahead and running it, if you wanted to know how I built it from scratch, that's also in a PDF that's inside of the demo of the repo, and you can go from there. I've made most of it available on GitHub, and also it includes that .NET data generator that I have there, which is run basically at a CLI level. Your Grafana dashboard configuration files, all your SQL queries for the panels, the setup instructions. Please feel free to fork it or modify it and adapt it for your own use. And let me know what you're monitoring with it, if it's IoT devices or your own fun time machine. Let me know from that. Yes. And as we wrap up our journey, I just wanted to revisit like these key takeaways. First, we've seen how to handle high cardinality using techniques like strategic key tag selection and structured queries, and time bucket aggregation. These approaches kind of ensure that it will be more performant. Second, we explored how to write data efficiently using line protocol and read it with SQL. And we've demonstrated how to scale from thousands to millions of data points without performance loss, because you learn techniques like downsampling or compression and to deciding what to move to cold storage when. Thank you for joining me on this time series journey today, and I appreciate your time.